Welcome back. So this is going to be the last video for our review for exam 3, and this video is going to be over fluids and pressure. So to start with, let's write down how we can define pressure. So pressure, which we denote with a capital P, is going to be equal to the force divided by the area. Okay. So there's a couple of symbols in here that are kind of similar to each other, so I want to highlight that quickly. This is P for pressure, which we say is a capital Latin P. We're also going to encounter the Greek letter rho when we get to the pressure in a column of fluid. And I just want to say right now that these are different symbols, even though they look kind of similar. Okay. So now that we have a definition of pressure, let's see what some of the things that we can do with it are. So look at this cylinder I have in the bottom left, and imagine that this is filled with some liquid to the top. And we'll say that it's closed to the top of the cylinder so we don't have to worry about atmospheric pressure. Let's figure out how we can find what the pressure is at some depth. We'll say that that depth is going to be a height h. Okay, so we want to find what the pressure is at this height h. Now, the way that we're going to do that is to use this definition of pressure, and we're going to calculate what the force is for that column of water. So to start with, we know that this has some height of h, and we're going to have some cross-sectional area for this cylinder of A. Okay, so in order to find what the force is, so we want to find what the force is. So the force is going to be equal to mg. But we don't have what m is, but we can find what m is from the volume of this amount of water here that goes down to this height of h. So this is going to go down to this height of h. And what the density of this is. So the density, which we write as rho, this is the letter that I was talking about, is going to be defined to be the mass per volume. Okay, so this is something that's inherent to a particular material or fluid. So you can have like the density of air, the density of water, the density of wood. Lots of materials have different densities. So here what we can do is we can say, I want to find what this mass is. So I can rearrange this equation to say that the mass is going to be equal to the density, rho, of the liquid, so this has some rho, times its volume. Now what I need to do is I need to write down what the volume is. Well, we have some cross-sectional area and we have some h, so V is just going to be equal to A times h. So the mass is going to be equal to rho A times h. Okay. Now let's see how we can combine this equation with this equation and this equation. So first let's plug in the rho AH into our force equation. So we have the force is going to be equal to rho AH times G. And then we can take this new equation that we have here and we can plug it into this equation. And so when we do that, we find that the pressure at some height h is going to be equal to rho AHG divided by A. Or this is going to be equal to rho times GH, which is the standard form of this equation. Okay. Now that we have this equation, we can see something really interesting. So let's look at this pressure equation. The pressure is going to be dependent on the density of the liquid, the acceleration due to gravity, and the height. It actually doesn't have anything to do with the area at all. So this is pretty interesting because what it tells us is that different size containers are not going to have a different pressure at the bottom as long as the height of the container is the same. And so what this carries us into is understanding Pascal's principle. So let's look at these two cylinders that I have here, and we'll assume again that these are filled with water, and we're going to ignore any pressure from the atmosphere. And so what we can say is if these both have some height h, then the pressures at the bottom of them are going to be P1 is equal to rho times G times H. The pressure from 2 is going to also be is equal to rho G H, because it's the same height, same fluid, we're still on Earth. So what this tells us, if I compare these, is that P1 is equal to P2. Now, this is interesting because we can consider what happens if I connect these two at the bottom with some tube. If the pressures are the same, there's not a difference in pressure. So there's not going to be any water that flows from left to right or from right to left. And what that means is that if I connect these two and these have the same height of water, that they're in equilibrium. And so this is interesting, again, because you would think, well, this is a big container and this is a little container. Maybe the liquid's going to flow from one to the other. It's not, as long as the heights are going to be the same. And so what we can do is we can combine what we found here with our original equation for pressure to say that the force for 1 divided by the area of 1 is going to be equal to the force for 2 divided by the area for 2. This is really interesting because the pressures are going to be the same for both of these containers. But obviously the forces aren't going to be the same because this is not a lot of water compared to this. This leads us to all sorts of interesting applications like jack. So how can you lift your car? Well, you use a jack, and the jack has a setup that's very similar to this, so that the small amount of fluid that you have in the lever arm that you're trying to push down on to lift your car is going to offset the weight of your car. The last thing that I want to talk about is what's called Archimedes Principle. What Archimedes Principle says is that the buoyant force F sub B is going to be equal to the density of a liquid times the volume that's displaced in the liquid. So this is the liquid, and this is displaced, times gravity. Okay. Now this is kind of interesting in and of itself because we had this relationship before between density and mass. And so what we can do is we can take this portion here and ask ourselves what is the mass that's associated with this. So this is going to be some m is equal to rho L times V displaced. So what this says is that this mass is going to be the amount, it's going to be the mass of water that's displaced by having an object in it. So really what Archimedes' principle says is that the buoyant force is going to be equal to the weight of the fluid that's displaced by the object that you're putting in it. So that's going to be it for our discussion of fluids. We've laid out all the equations here. I wish the best of luck for everybody on the exam, and good luck studying.